My slide is visible to all of you.
Yes, sir.
So we're talking about the ohm meters. And we had already discussed one of the ohm meter. That is your series type ohm meter. We discussed it in detail. Now we'll discuss the shunt type. We were discussing the shunt type ohm meter. So this is the circuit diagram for the shunt type ohm meter. And on that day, on the last turn. So for extreme values of Rx, when Rx is equal to 0, then obviously it is shorted and no current will flow through the meter. So the deflection will be 0. And when Rx is open circuit, so all the current will flow through the meter, and it will give you obviously the full deflection, full scale deflection. And in this case, the design is very easy. In this case, we have to means when it is open, then we have to ensure, as far as design is concerned, we have to ensure that only that much current should flow, that is maximum, that should be equal to the maximum allowable current through the meter, and that is obviously is the full scale current. So this is a series circuit, and um, we know the full scale current, input current of the meter. With this equation, we can very easily design this circuit. Means we have to design the calculate the value of RSE, that is calculated, and design is done. So this is only the means like series type ohm meter. Here we don't require much because only one parameter we have to calculate as far as designing is concerned. But some other conclusion will draw from this derivation. We are making a derivation, and that will draw some important. It is not for the design. That's what I want to say. Now, with terminals AB connected across the resistance and the test Rx, the battery current, in this case, when there is a AB is not written here anyway. I'm just putting it. Means when your some Rx is there, so this is basically your AB. This is A, and this is B. Sorry. So the battery current drawn, this is your battery current. So obviously your battery current will be the V divided by equivalent resistance. So equivalent resistance will be obviously these two are in parallel. Your RM and Rx are in parallel, and this parallel combination is series with the RSC. So that's what I had written here: V upon RSC plus RM Rx upon, and then meter current. This is the total current drawn from the battery IB. Now we are interested in expression for meter current. This is your meter current. Oh, sorry, this is your meter. This is your meter current. So current divider theorem you must have studied earlier, that this is the total current. Then in a parallel circuit, parallel branches, this current is dividing into IM and some other current through the unknown resistance. So we are not interested in the current through the unknown resistance, but we are interested in current through the meter resistance. So obviously current divider theorem you must have studied, that is equal to IM will be equal to total current, that is in this case it is battery current drawn from the battery, into the resistance of the other branch, that is Rx, upon Rx plus Rm. This is basically the current divider equation, you can say, or this is what is the meter current. So that's what I had written here. This is that term that I had written, and this is your IB from above expression. This is your battery current. So after simplification, we got this one. Now we are taking this ratio. If you look upon this ratio, this is basically normalized meter current. Normalized meter current means you are normalizing the meter current. You are dividing the meter current. This is a ratio of two currents. This is the ratio of meter current to the full scale meter current. So you are basically normalizing the meter current by the full scale meter current, or you are dividing the meter current by full scale meter. We are taking this ratio that we are calling S. So this ratio obviously will vary as your meter current will vary. Only thing it will make the variation will be between 0 and 1, and 0 and 1, because maximum current will be IM, maximum value of the IM will be IFM, and minimum will be 0. So the variation will be between 0 and 1. That's what we have done here. So this ratio is basically the normalized meter current only. So then we took this ratio. So IFM we took from equation 1, this, and IM from here, this one, this expression. So we took the ratio of these two expressions, and then we simplified it, and we kept on simplifying, and then we reached to this expression. Now this RSC into RM, we replaced it by RP, where RP is equal to RSC. And so if anybody is having any question regarding these expressions, you can ask, please. Then we'll go to the next level. So this is finally we reach to this expression after simplification, and then one expression is replaced by equivalent resistance, you can say equivalent resistance RP, that I put here. Anyway, the halfway mark on the scale occur when Rx is equal to Rp. You see, if you look upon this Rp, so Rp is nothing but the equivalent resistance across the input terminals. If when you look into this, and you short it, remove this voltage. So the resistance that will equivalent resistance that will be appear here, it will be Rp actually. And obviously in this circuit means then we can write it like this: the equivalent Thevenin equivalent resistance, that is approximately V will be here, and I'm putting it V Thevenin. Then this will be Rp. This will be Rp, and this is Rx. So obviously half scale current will flow when half of the current, total current, battery current, will be drawn from here, IB upon 2. So for that, these two should be equal. So that's what it is written here, that halfway on scale occur when Rx is equal to Rp. So half a, so obviously RH is equal to Rx is equal to Rp is equal to RH. So the RH will be equal to this resistance. Now, when this is one thing, now I'm coming back to this expression. When Rx is very small in comparison to Rp, this is very important thing I'm talking. When Rx is very small in comparison to Rp, then obviously Rx can be neglected in comparison to Rp in the denominator, because Rx is very small in comparison to Rp. So obviously then S will be approximately equal to Rx upon Rp, where Rx upon Rp, where Rp is constant and Rx is a known value. So, and S is basically the meter current. So we can say that S is proportional to Rx. So whenever you have this kind of relation between the operating current and the parameter you are measuring with the meter, the scale will be linear or uniform. Linear means uniform. Uniform means you must have seen the scales of different meters, that sometimes you'll find your divisions are equal throughout the scale. So this kind of scale need this kind of relation. Sometimes you'll find that so this kind of scale is called uniform scale. And sometimes you'll find your scale is not, divisions are not same throughout the it is very close at the starting, then as we go for the higher scale side, then distance between divisions increases like this. So this is called one kind of non-uniformity. In some scales, you will find your divisions are very close at the starting. Your division are very close at the end, but in between it is at the larger distance. So this kind of scale, these kind of scales are called non-uniform. And obviously, it is easy to read the uniform scale in comparison to non-uniform scale. So generally, we prefer that the our scale should be uniform, but it depends upon the meter technology, what kind of meter you are using. Like permanent magnet moving coil instrument, voltmeter and ammeter, they are having uniform scale, and this is not true for moving iron type of instrument, because of the square law it follows. So anyway, so this here, this with this approximation, we are able to draw one conclusion, that the meter current is directly proportional to the unknown resistance at the lower values. So out of this finding, we are able to conclude this thing. This type of ohmmeter is particularly suitable for measurement of low value of resistance, because if you are making a ohmmeter for measurement of low value of resistance within the medium range, then this type of meter will have uniform scale. Otherwise, it will be it will have non-uniform scale. So this is how we are able to analyze the normalized current expression, and we reach to this conclusion, that this type of, otherwise if you want a larger range ohm meter using shunt type ohm meter, then your scale will be non-uniform. So this is what I suppose to discuss in this topic. If you are having any question, anything you are not able to understand as far as the shunt type ohm meter and series type also ohm meter is concerned, you can ask, please. Today I'll put these slides on Classroom, whatever I have discussed, and you can go through these slides. And if you are having any issue in any of the topics that I taught you, that you can ask on the next turn. Okay. So anyway, I'm closing this topic today. So now I'll summarize because one section of this unit we had already finished, and then today we will switch over to the next part of the unit. So we started. This is the broadly. This is basically measurement of. We were discussing the measurement of. Just a minute. Measurement of medium resistance. So in measurement of medium resistance, first of all, we discussed voltmeter ammeter method, and all the final points we have discussed about that method. Then we discussed your substitution method. This substitution method is better than voltmeter ammeter method, because whatever drawback your voltmeter ammeter method was having because of the use of two instruments, that is taken care of in in substitution method, because it utilizes only one instrument. Then this method is also having a problem of because it is a two-step method. So if there is any variation in excitation, that will lead to the error in your result. So to take care of variation in lead resistance, then we discussed third method, that is your Wheatstone bridge method. And Wheatstone bridge method, when used in the null mode, then its result does not affect with the because of any variation in excitation. Once your bridge is balanced, if there is any variation in excitation, it won't affect the balance condition. So this is considered, actually Wheatstone bridge is considered as the best method for measurement of medium resistance. Then when your resistance is dynamic, means it is changing in time with time, and this change is fast, then null mode of operation of Wheatstone bridge cannot be used, because balancing takes time, even if it is automatic balancing. So we discussed the deflection mode and two configurations of bridge that suits the dynamic for dynamic measurement. That is your voltage sensitive bridge and your current sensitive bridge. But whatever privilege of independence to the variation in excitation your null mode was having, this deflection mode of operation will not have that privilege. So all these things we discuss in Wheatstone bridge. Again, I'm telling you, Wheatstone bridge is basically best method for measurement of medium resistance. Then we discussed ohm meter. Ohm meter is a method or a instrument. It is a direct reading type method. In this method, it is user friendly kind of method. Means anybody can use it, because you are not required to have a technical knowledge about the method. So because it is direct reading type, but it is not as accurate as any of the method we have discussed. It is means easy to use method, and it tells the approximate value of the resistance. So if you require for general purpose measurement, ohm meter is fine. But if you require very accurate, then you have to use obviously the best method, your bridge method you can use. So this is whatever we discussed from the starting till today in this unit, that I recapitulated. And these all methods that we have discussed, four methods we have discussed, they are all used for the medium resistance measurement. Now we'll discuss the small, because at the starting I told you that the large measurement of larger value of resistance and smaller value of resistance, or by the matter of fact, any parameter, very small value and very large value is always a challenge. Accurate measurement is always a challenge. Every parameter have its own challenges. So the small resistance measurement is also having its own challenge. So today I'm starting with the challenges in measurement of accurate measurement of small resistance. Means if we are using these methods which we have used in the for measurement of medium resistance, then how these resistance won't fetch the accurate result, although they were fetching giving us accurate result for medium resistance. But if you are using small resistance, then it won't give you good results. They will give you erroneous results. So first of all, we'll discuss what are the reasons, what are the challenges, what is the limitation that these method will. So obviously range we had decided, range we had this means earlier it was told that less than 1 ohm resistance is considered as the medium resistance, as a small resistance. So we are talking about that. So now we are coming to measurement of small resistance, and very first point uh, that gives you the reason what is the challenge, why these methods whatever we have studied won't fetch us accurate result. So small resistance measurement challenge is basically the resistance of lead and contact. Resistance of lead and contact means what? Because you are making a circuit, you want to measure a resistance, and then you are connecting this resistance, unknown resistance. You are making a connections using leads. So these lead resistance, and then you are connecting it somewhere, and the contact resistances, they are mean source of error. तो आप कहेंगे तो लीड तो मीडियम रेजिस्टेंस में भी यूज किया जा रहा था, तो वहां क्यों नहीं प्रॉब्लम क्रिएट करता है? Yes, because medium resistance is comparatively large resistance. So these resistances were not making much difference. As I told you earlier also, that if you are weighing a kg of apple, and the error in measurement is suppose 1 gram, so it is 0.1%. But if you are measuring your 10 gram of gold, error of 1 gram is 10%. So that's why error is basically expressed in percentage. That is what is the reason. So that kind of situation here is also, you see, that's what I had given. If we are measuring 100 ohm, so contact resistance is 0.02 ohm. So you can see that it is very small in comparison to the resistance we are measuring, your contact and lead resistance. But if your resistance is 0.02 ohm and your lead and contact resistance remains same, so your error is you're getting 10% of error, and it is not acceptable. 10% of error is very high. In general purpose measurement, generally 1% error is required. Okay, so this is one of the reason. This is not one of the reason. This is the main reason why what is the challenge in measurement of small resistance. It is lead and contact resistance. And you see, we require a method which deals with which can tackle these source of error. Only then you will get the correct result. So obviously, your whatever method we have studied in its original form, they are basically not made for the low resistance measurement, so they won't cater the issue related to the low resistance measurement. So you have to modify them so that you can. So here you see low small resistances are many times you will find they are four terminal resistance. If you go into the market and you want to purchase a small resistance, then you can ask for the four terminals. So it is having two current terminals and two potential terminals. These potential terminals are very close to the resistance. And so in this case, your this circuit, you see these are the two current terminals, C and C dash, and P and P dash are the potential terminal. So if we are using low resistance with the help of with the help of voltmeter meter method, then we'll connect the meter like this, and we'll connect the voltmeter across the potential terminal, because potential terminals are very close to the resistance, so the wire lead is not coming in between, so that otherwise your voltmeter reading will include the voltage drop across the lead also. And as far as the lead which is connecting the, means if we are connecting suppose voltmeter here like this, so obviously whatever voltage drop take place in these leads, that will also be counted here. But as far as this lead is concerned, because your voltmeter is having very high internal resistance, so the current drawn is very small. This IV will be very small, so the lead drop will be negligibly small. So that's what is the concept. But still, you see, voltmeter ammeter method is not a good method. I mean, even in medium case. So all those problems which we were having error, which we were having in case of medium resistance measurement, those will present here also. Although we have taken the lead resistance and contact resistance potential, the error in measurement of means because of the lead resistance drop and contact drop, that we have taken care of up to some extent by having a four terminal resistance, but still there is the issue. So this is basically called voltmeter ammeter method for measurement of low resistance. So for measurement of low resistance, these are the different methods which are used. Voltmeter method that we had discussed just now, for with the help of with four terminal resistance, that we have discussed. Now the best method for measurement of voltmeter ammeter for measurement of low resistance is Kelvin's double bridge. It is a bridge, and it is basically modification of Wheatstone bridge. So when Wheatstone bridge is modified to take care of lead and contact resistance, then it becomes Kelvin's double bridge. So it is basically modified, and I'm trying to make you understand how it is. Kelvin's double bridge is means how we can modify. What is the process? How can we make with the modification the Wheatstone bridge, which takes care of lead and contact resistance. Now I had shown you Wheatstone bridge here. Be careful. This is a very, very important thing I'm discussing. So this is, you see, this is your Wheatstone bridge. These two are called ratio arms. And this is small resistance, unknown resistance, and this is standard resistance. Generally, to make the bridge balance, we require a standard resistance of same range, means value of the standard resistance should be of the same range as that of unknown resistance. So obviously your standard resistance will also be a small resistance. Now the source of error is the lead in arm R and in arm S and the contacts of these leads. You understanding what I'm saying? Now, if we are considering this is the lead and contact resistance, this R is the lead and contact resistance that is causing the problem. So obviously we want that our final, because R is present here, so our final result should be free from contact resistance. Our final expression should be like this. But if we look upon, if I am connecting galvanometer here, so your contact resistance, lead and contact resistance will be added with S. So your balance equation will be something like this. And if we are connecting galvanometer here at N, then this lead and contact resistance will be added with R. Our balance equation will be like this. लेकिन जब हम जब कैलकुलेट करते हैं, अब जब हम जनरल मेजरमेंट टेक्निक जो है, जो प्रोसीजर है, उसमें हम ये करते हैं कि हमने ब्रिज को यहाँ अननोन रेजिस्टेंस लगाया, ब्रिज को S को वेरी करके ब्रिज को बैलेंस कर लिया. अब हमको P की वैल्यू मालूम है, Q की वैल्यू मालूम है, S की वैल्यू मालूम है, जिसपे ब्रिज बैलेंस हुआ, और हमने इस इक्वेशन में डाला और हमने रिजल्ट कैलकुलेट कर लिया. बट वी आर नॉट कंसीडरिंग इन our equation, we are not considering the lead and contact resistance, and it is there. So obviously the actual balance equation will either be this or it will be this. But if we are not using these balance equation with the considering the lead and contact resistance, this equation will fetch us the erroneous result, है ना. जो R की वैल्यू आप इस इक्वेशन से कैलकुलेट करेंगे या इस इक्वेशन से कैलकुलेट करेंगे, और जो R की इक्वेशन आप इस इक्वेशन से कैलकुलेट करेंगे, दोनों में डिफरेंस होगा बिकॉज ऑफ द लीड एंड कॉन्टैक्ट रेजिस्टेंस, एंड दिस विल लीड टू द एरर. जो भी डिफरेंस होगा वो एरर कहलाएगा. अब आप कहेंगे कि साहब ये प्रॉब्लम तो मीडियम रेजिस्टेंस में भी थी. तो मीडियम रेजिस्टेंस की वैल्यू देखिए ज्यादा होती है, यही वाला इशू है. मीडियम रेजिस्टेंस की वैल्यू ज्यादा होती है, स्मॉल रेजिस्टेंस की वैल्यू कम होती है. तो यहाँ पे लीड एंड कॉन्टैक्ट रेजिस्टेंस से जो एरर होगा दैट विल बी सिग्निफिकेंट, एंड वी हैव टू कंसीडर, टेक केयर ऑफ इट. तो एक तरीका तो ये है कि लीड एंड कॉन्टैक्ट रेजिस्टेंस हम मेजर कर लें, और दैट इज नॉट बेसिकली पॉसिबल ऑल्सो, एंड दैट इज नॉट feasible also. So we require a compensation. How can we compensate it? तो ये बात जो मैंने अभी आपको बताई कि अगर लीड रेजिस्टेंस को अगर स्मॉल अननोन रेजिस्टेंस को अगर व्हीटस्टोन ब्रिज से मेजर करते हैं, तो क्या प्रॉब्लम आएगी बिकॉज ऑफ द लीड एंड कॉन्टैक्ट रेजिस्टेंस. ये बात आपको समझ में आएगी नहीं?
यस सर.
आगे बढ़ूं मैं?
यस सर, समझ आ गया सर.
ठीक है. Now what is the solution? That solution, a solution has been proposed that instead of connecting
एक क्वेश्चन था कि सर स्मॉल आर मतलब लीड एंड कॉन्टैक्ट रेजिस्टेंस को हम लोग उस साइड क्यों नहीं कर सकते, पी और क्यू के साइड क्यों नहीं कर सकते?
दिस इज तो जरा अपना
हेलो सर,
अपना माइक्रोफोन म्यूट कर लीजिए आपको, क्योंकि इको हो रही है मेरी आवाज. देखिए मेन इशू इसमें है क्योंकि ये रेजिस्टेंसेस छोटे हैं, है ना. ये आप, इसीलिए हमने उतने टाइम एम्फेसाइज किया था कि R इज अ स्मॉल वैल्यू, S इज आल्सो इन स्मॉल वैल्यू. only then means if your S is not in the same range, you cannot balance the bridge for given value of P and Q. So generally value of the ratio arms resistances are taken medium resistance values, means 100 ohm 200 ohm, there is no issue. तो यहाँ पे लीड रेजिस्टेंस का कोई इशू नहीं, क्योंकि आपका जो रेजिस्टेंस है वो इन कंपैरिजन टू लीड रेजिस्टेंस बहुत हाई है. So here we neglect lead and contact resistance as far as arm P and Q are concerned, because their resistances are value are high, because we don't require. But as far as the arm R and S is concerned, their values are small, so their lead and contact resistance are having a significant contribution in balance equations. So that's why I had shown here the R and small r we are considering either with R or with S, because these lead and contact resistance are significant in comparison to their known counterpart or unknown counterpart or the bridge resistance counterpart. बात समझ में आई कि हमें इसका कंपनसेशन की जरूरत नहीं, क्योंकि यहाँ पे पी एंड क्यू की वैल्यू हम मॉडरेटली हाई लेते हैं. बात समझ में आ गई? आप लो ले सकते हैं, लेकिन लो लेने से फिर वो इशू यहां पे भी आएगा. बात समझ में आ गई?
यस सर.
तो यहां पे देखिए, ये जो हमने सिचुएशन कंसीडर की है, ये भी हाइपोथेटिकल सिचुएशन है. आपका जो लीड एंड कॉन्टैक्ट रेजिस्टेंस होता है वो डिस्ट्रीब्यूटेड होता है थ्रू आउट द वायर. ऐसा नहीं कि एज ए कंसंट्रेटेड आर है, लेकिन हमने इसको यहाँ पे इसको रिजॉल्व करने के लिए यहाँ पे अज्यूम किया है कि इट इज अ लम्प्ड रेजिस्टेंस ऑफ वैल्यू स्मॉल आर. बात समझ में आ रही?
यस सर. यस.
तो अब हम इसका सोल्यूशन, किसी ने ये बताया साहब कि if instead we are not required to connect galvanometer at M or at N, when we are connecting a galvanometer at N, then this R is going with S, and when we are connecting it at N, then R is going with R. So in any case, it will have a if we won't consider its value in balance equation, then whatever value we'll calculate through the balance equation, this balance equation, it will be erroneous. So wherever we connect, whether we connect at M or we connect at N, in both the cases, the measured value will have the error. So it has been suggested that instead of connecting galvanometer at M and N, we connect the galvanometer somewhere in between the M and N, so that this connection should divide the lead and contact resistance in two parts, R1 and R2, in such a way that ratio of R1 and R2 is equal to ratio of P and Q. Then this lead and contact resistance won't affect your final outcome. This is what is the solution that has been suggested, that ऐसे आप लगाइए कि R1 ratio of R1 upon R2 should be equal to P upon Q. If this condition is satisfied, अभी देखो, अभी हम उसमें नहीं जा रहे हैं कि ये कैसे किया जाएगा. अभी तो हम सारी सिर्फ सोल्यूशन की बात करें. If this is done, obviously that how this can be done, that is a challenge, but that is not point of discussion at this moment. So if this condition is met, then your lead and contact resistance will not come into the picture, that small r will not come, and your balance equation will be clean like this, and you can very easily calculate, and your result will be unaffected by it. So this is what is the solution that has been. Then we'll try to find out कि ये solution काम कर रहा है नहीं कर रहा है ना, कि कह रहे हैं साहब ऐसी इक्वेशन आएगी, बैलेंस इक्वेशन, क्लीन बैलेंस इक्वेशन आएगी, एंड इट वोंट अफेक्ट योर बैलेंस, योर लीड एंड कॉन्टैक्ट रेजिस्टेंस. तो इसको चेक करते हैं. सो दैट्स व्हाट इट इज रिटन हियर. सो दिस इज द कंडीशन. तो ऑब्वियसली जो बैलेंस इक्वेशन होगी वो ये हो जाएगी, देखिए.
यस सर.
आर के साथ R1 आ जाएगा और S के साथ R2 आ जाएगा. तो ये तो अभी भी मौजूद है यहाँ पे. क्योंकि स्मॉल r1 and स्मॉल r2 या स्मॉल r मेजर करना प्रैक्टिकली पॉसिबल नहीं है, बिकॉज इट इज डिस्ट्रीब्यूटेड. नाउ विल सी. तो अब इसको फर्दर हमने कुछ करने की कोशिश की है. दिस इज द बैलेंस इक्वेशन इन द सजेस्टेड मॉडिफाइड व्हीटस्टोन ब्रिज. तो हमने रेशियो ले लिया r1 अपॉन r1 प्लस r2, और फिर हमने न्यूमरेटर एंड डिनोमिनेटर r2 से डिवाइड किया. सो वी आर गेटिंग p अपॉन, और r1 एंड r2 इज इक्वल टू p अपॉन q. ये कंडीशन है, ये कंडीशन. तो p अपॉन q, तो फाइनली वी आर एबल टू फाइंड r1 in terms of p, q and r, because p, q and r are basically the original parameters. So r1 is translated into p, q and r. Similarly r2 को भी हमने ऐसे ही किया. r2 upon r1 plus r2 रेशियो ले लिया. Then r2 is defined in terms of p, q and r. Now we'll put the value of r1 and r2 in this equation. Then you see we are putting it here, and finally p upon p plus q is coming both side, and it is cancelled. So r is equal to p upon p plus q. Now I want your comments. Your comments, please. जी आप बताइए.
So now the equation is free from that particular dependency of R1 and R2.
Means lead and contact resistance are not coming in final expression, so their effect is taken care of. So this is what is the modification that has been suggested in Wheatstone bridge that leads to the compensation of effect of lead and contact resistance. Although the way I had described it, it is a theoretical way, and there is still a challenge how to implement this scheme, because this is not practical. Means finding the point D, because it is not a variable resistance. It is a distributed lead and contact resistance. So how will you find the point D so that you can connect the your galvanometer? This is a challenge. So practical implementation of this modification is a challenge, and that Kelvin's double bridge is basically practical implementation of this concept. Okay, so now I'll show you the practical implementation. If anybody is having any query regarding this modification or this concept that I had discussed, you can ask, please. Anyway, I'm taking the attendance. You try to absorb whatever I explained about the inception of Kelvin's double bridge or modification or in the Wheatstone bridge. Then after attendance, I'll means if anybody is having any query regarding it, then I'll explain it. Otherwise, I will show you the implementation of this concept, physical implementation. Respond to your roll call. You keep thinking. I have shown the slide here. You absorb it. Rule number 1. In this case, how can we implement it? I'll showcase you quickly, and then you instead of having means what we do, you see here, it is P, it is Q, that is your ratio arms of this, and we take real resistances. These are the R and S, and these are obviously small resistance, so they are having 4 terminals. They are having 2 potential terminals and 2. So one potential terminal is connected to P and Q, and second set of potential terminals are connected to the galvanometer. So D point of contention is point D, from where you will get the point T. So instead of dividing the unknown, your lead and contact resistance, here this is a real lead and contact resistance, lead, the real lead is here. So instead of finding the D somewhere here, what is done, we take another set of resistances, P and Q, small p and small q, and the junction of these small p and q is basically the point D to which your galvanometer is connected. And um, and another set of your galvanometer, sorry, your lead resistance, potential terminal of, sorry, your unknown resistance and standard resistance are used to connect these small p and q to the resistances. So this is the way. Instead of finding the D, we take another set of the physical resistances, real resistances, small p and q, and junction of these small p and q is point D to which your galvanometer is connected, and another terminals of p and q are connected to another potential terminal available with the R and S. So this is how this implementation is done. And obviously now in this case, implementation case, it is very easy to choose two resistances, small p and q, which are equal to capital P and Q, your original ratio arms, original P and equal to P and Q. It is very easily possible. And it is claimed that this implementation will have same effect as that of your modified Wheatstone bridge or conceptual modified Wheatstone bridge. And when you will balance the bridge, and this is called Kelvin's double bridge. And why it is called Kelvin's double bridge? Because it is having two sets of ratio arms, capital PQ and small pq. That's why it is called Kelvin's double bridge. Now tomorrow or on the next turn, we'll discuss, we'll verify whether this implementation fetches the same result as that of conceptual modified Kelvin's double bridge to compensate lead and contact resistance or not. Okay to all of you?
Yes, sir.
Yes, sir.
We'll start our discussion on the next turn from here. Okay. Now remaining